Hello my esteemed viewers. In this tutorial we continue with problems, of course with moderate complexity. In the previous tutorial, that is tutorial number 4, we have covered simple problems which are illustrative examples for normal stresses and normal strains applicable to simple cases, be it a machine or be it a structural component or whatever. As far as this tutorial is concerned, it has a special significance because the problems are of moderate complexity, number one. Number two, the problems that have been chosen here in this tutorial will bring to fore the significance of strength of materials in our day-to-day lives or in our mundane life, be it a handbrake in a moped, or be it a simple cutting plier, and be it a epoxy joint that is provided for concrete slabs, and be it bearings that are provided over a bridge in order to seat the superstructure of the bridge, and a column of a typical configuration as far as area of cross section is concerned. There is going to be a great learning in terms of the learning which are more than one. One is how significant it is the subject is in our real world problems. The first, the problems are of course cumulatively numbered, and in the previous tutorial we have covered around 7 problems. Therefore we continue from 8th problem. A force P of 70 Newton is applied by a rider to the front hand brake of a moped. This is the front hand brake. P is the resultant of an evenly distributed pressure. This is an assumption, of course. As the hand brake pivots at A, this is the pivot provided which can rotate. A tension T develops over here, and this is the cable which runs down and which is responsible for application of the brakes. In the 460 mm long brake cable, and the length of this cable is 460 mm, and area of cross section being 1.075 mm square, which elongates by 0.214 mm. Find the normal stress and strain in the brake cable. Of course, in this figure we cannot see the cable because cable is provided with a sheath, but it runs over here. When uniform hand pressure is applied over this through our palm, this pressure can be seen as a total force going in this particular direction, and this will cause some kind of a rotation over here and a tensile force in this cable. This is the hand brake pivot, which can with respect to which this brake lever can rotate, and here is the cable where tension force will be developed. Something like this, and it has a moment arm with respect to this pivot which is given to be 37.5 mm, and this has a moment arm with respect to this particular lever amounting to 100 mm. Therefore, when the full brakes are applied, when brake is fully applied, the system will go for equilibrium. Therefore, we can apply algebraic sum of moments with respect to this particular pivot should be equal to 0. Okay, we can apply that because brakes are fully applied by uniform pressure, and it will be converted into a total force, and here this total force induces some kind of a rotation in this direction over here, and this rotation in turn causes pulling of this brake cable. Therefore, sum of the moments about A equal to 0. Therefore, T tensile force going like this, okay, into 37.5 equal to P into 75. Okay, here it is acting at the center of this uniform pressure because this is the total force. It is 50 here till here plus 25, so that becomes 75. Therefore, we have brought in some kind of a relationship between T, the tension force acting in the cable, and the applied pressure. Therefore, sigma equal to T, that is the tension in the cable, divided by area of cross section. And the tension in the cable is 2 times the pressure. and pressure applied is 70 Newton. Therefore this becomes 2 into 70, 140, divided by area of cross section of the cable is also given. It is 1.075. Thereby we will get the amount of stress, the magnitude of stress, tensile stress acting in the cable to be 130.23 MPa. And we need to find the normal stress. Normal stress is found out. Normal strain is nothing but change in length divided by brake cable, that is the tension, the stress, the elastic modulus. Okay, the change in length is 0.214 elongates by dl, and this is 460. Okay, so that gives us the strain equal to 0.00047. Okay, that is the thing. Okay, this is strain is dl by stress. Okay, E equal to elastic modulus equal to 130.23, that is the stress divided by the strain. Okay, and that is, this is change in length by original length. Strain is change in length by original length, 0.214. Sorry, I told a different thing. 460 is the length of the original length of the cable. So we got this strain, and we can directly apply this stress, known stress and strain, in order to compute the elastic modulus. So elastic modulus is 2.8 into 10 to the power of 5 MPa. Of course, we need to write MPa because as we remember, the magnitude of elastic modulus is also same as the stress. Okay, we'll go for the next problem, the 9th problem. For a cutting plier shown in figure, if A equal to 90, that this moment arm, okay, and B equal to 40, and we will just explain that, and ultimate shear stress in the 6 mm diameter pivot is 320 MPa. What is the maximum value of the applied load P if the factor of safety is 3.5 with respect to failure of the pivot is to be maintained? So applied force is tau, that is, see, this is the system. First of all, let us understand how exactly cutting plier works. In a typical cutting plier, when we apply the forces like this uniformly to the handle, the cranky shaped arms, okay, and the arms will go like this. Arms will go like this. See, here is one arm which takes a turn and it comes over here, something like S shaped, and here also the other arm will go like this. So this has been articulated into this shape for a better understanding. So this is this arm which is being written. Okay, and whatever the thing happens for this arm will also happen for the other arm. Therefore it is enough if we write the free body diagram of one arm. Here is the force P applied, and here is a point that is called as a fulcrum or the pivot. When the force is applied like this, this is going to rotate for a while, as long as these 2 points will come to a touch, and this rotation will also cause after the rotation, it will cause a shear force within the needle or within the stud that is placed over here. We cannot see in this figure, but inside there is a pin which runs and which holds these two arms, and the shear force will go like this, and this is the P. When the pressure is fully applied, complete pressure will be put onto this particular piece of specimen that is placed over here, and the system will be in equilibrium. So F equal to tau by A, and we have computed tau is given. Okay, 320 MPa, that happens to be ultimate shear stress. Therefore we cannot take ultimate shear stress directly. Factor of safety is also given. Therefore we divide ultimate shear stress by factor of safety in order to obtain working shear stress. It is working shear stress into area of cross section of the needle or of the pivot or of the stud which is subjected to shear. So the force that will play on this small needle which is somewhere over here is 2585 Newton. And if we apply, we know this force, we can compute the force that is being applied. So P into 130 till here. Okay, 90 plus 40, 130 equal to 2585 into 40. So we will take moment with respect to this, because it can move, it can rotate with respect to this point also, of course, towards this particular point. Therefore we will apply this principle of moments, or sigma m equal to 0, because when the pressure is fully applied, even the levers will also come to an equilibrium stage. So therefore P will be evaluated to 795.4 Newton. Imagine the next question goes like this. Imagine that a long wire of tungsten hangs vertically from a high altitude balloon. What is the greatest length in meters it can have without breaking if the ultimate strength is 1500 MPa? If the same wire hangs from a ship at a sea, what is the greatest length? Given density of tungsten wire is 190 kilonewton per meter cube, the density of sea water being 10 kilonewton per meter cube. So here the thing of interest is the self weight matters here. Self weight matters the most, of course, because the length is too much. As the density of steel is very high, density of steel is also very high, to the tune of 75 kilonewton per meter cube, while the density of tungsten wire in this example is much more than that, 190 kilonewton per meter cube. That means 1 meter cube volume of tungsten would weigh 190 kilonewton. Therefore it is going to elongate by virtue of its own weight. But okay, we will calculate that. First of all, the first question we will answer: wire hanging in air. We need to find out the weight. Weight is nothing but volume of the wire into its density, the material out of which this particular wire is made. So this is density of tungsten into area of cross section into length. So therefore sigma equal to weight by area. So weight is written over here and area of cross section is over there. Since the diameter of the wire is not given, this area and this area and this area will get cancelled, and we will be left with density of tungsten into length. And density of tungsten is given to be 190 kilonewton per meter cube. This is 190 into 1000 to make it Newton, and we have divided this by 10 to the power of 9 because it is meter cube over here. We need to convert that into millimeter cube as per SI units. So 1000 millimeters equal to 1 meter. Therefore it is 1000 into 1000 into 1000. That makes it 10 to the power of 9 into L is there. Therefore upon cross multiplication, and of course the stress is given to us 1500 MPa. Therefore we equate this and we will just get the length in terms of millimeters, and when we divide this by 1000 we will get 7895 meter. We can afford to have this much lengthier tungsten wire which is freely hanging in air. On the other hand, if we just submerge this tungsten wire in water, of course water will come up with buoyancy. It's going to have some kind of an uplift pressure. Okay, it's going to reduce the weight to some extent. The reduction in the weight comes from the fact of its unit weight or its density, so that should be negated. So volume of wire, so weight of the wire equal to volume of the wire into density of tungsten minus density of water. Because density of water, by virtue of density of water, this particular wire will experience some kind of a buoyancy, some kind of an uplift. This will reduce the weight of the tungsten wire, which otherwise it would have had, by some amount. This magnitude is given over here. Therefore stress equal to weight divided by area. Weight is unit weight of tungsten minus unit weight of water, or density of tungsten minus density of water into area of cross section into length. This will speak of volume divided by area. Area will get cancelled once again, and we will be left with stress equal to 1500 equal to 190 minus 10. 190 that of tungsten and 10 that of water. It is multiplied by 1000 to make it Newton and divided by 10 to the power of 9 in order to make it Newton per millimeter square, and length remains over here. Upon cross multiplication and upon further simplification, we will get a length of 8333, and of course a huge increase in at least 1000 meters, just because this is immersed in water. a joint between two concrete slabs A and B, this is the 11th problem, filled with a flexible epoxy like this, that bonds securely to the concrete. The height of the joint is, this is the joint is, that is thickness of the slab. It should be equal to thickness of the slab because it should cater to the entire thickness of the slab. It is 100 millimeter. Its length is 1 meter here like this, and its thickness is 12 millimeter. This is the thickness of epoxy joint. Under the action of shear forces V, the slabs displace vertically. Okay, if it moves horizontally, it's going to compress the epoxy. On the other hand, if it moves vertically, it's going to induce shear stress in epoxy. It moves vertically through a distance of 0.048. This is the dislocation. And you may recall that whenever we define shear strain, it is the amount of dislocation per unit height. Dislocation of a point at the extremity relative to each other. What is the average shear strain in the epoxy? What is the magnitude of forces V if the shear modulus of elasticity G for the epoxy is 960 MPa? And we recall Hooke's law is applicable even for shear stress and shear strain also. Under elastic limits, shear stress is proportional to shear strain, or shear stress linearly varies with shear strain, which brings in another measure of rigidity called as modulus of rigidity. Should be modulus of rigidity within elastic limits, of course, is related to shear. Okay, and here is a slab, and here is the epoxy. It moves vertically down, and it configures, it deforms the epoxy in between, something like this, because of owing to the downward movement of one of the slabs due to relative moment. Therefore, average shear strain is the amount of dislocation that is given over a thickness. Okay, and if you go back, this is the thickness. We should be seen as the height, and this is the dislocation. Earlier it was there, this point is over there, it has slightly come down, and that is directly given to be 12 millimeter, no, not 12 millimeter, 0.048 millimeter. So the dislocation of this point till here is 0.048. It happens over a thickness of 12 millimeter. So that will give us the shear strain, amount of dislocation of the point divided by the original height. 0.004 is the shear strain, and shear stress can be directly calculated because we know the rigidity modulus or shear modulus, which is given to be 960 MPa. So 960 MPa into shear strain will give us the shear stress that is developed in the epoxy. Therefore, shear force is shear stress into area, and shear stress is shear stress into area, and the area is this. This is length, and this thickness, this height. Length into height will form cross-sectional area which is subjected to shear as far as epoxy is considered. Therefore, shear stress is 3.84, and the area subjected to shear force is 100 into 1000, 1000 being the width, 100 is going to be the depth. Therefore, it will give us the magnitude of shear force. Then a flexible connection connecting rubber pads. See here like this. These are all rubber pads. So there are 1, 2, 3 rubber pads are connected. Thickness equal to 9 millimeter, bonded to steel plates. They are all steel plates, 1, 2, 3 steel plates, and there are flexible rubber pads marked in yellow. Their thickness is 9 millimeters. Bonded to steel plates is shown in figure. The pads are 200 millimeter long and 150 millimeter wide. And in order to see the width, you have to take a section like this. Okay, and the length is available over here only. So from here till here, it measures 200 millimeter long, and across this it measures 150 millimeter wide. Find the average shear strain in the rubber if the force is 15 kilonewton and the shear modulus of rubber is 830 kPa, kilopascal. Find the relative horizontal displacement between the interior plate and the outer plates. interior plate and the outer plates. And here is the thing, and if it is P, it's given only over here for the equilibrium concerns. If this is P, and here it should be P by 2 and P by 2. When we apply sigma fx equal to 0, minus P by 2 minus P by 2, it becomes minus P equal to plus P. They will cancel and the system will be in equilibrium, but they are going to cause some kind of a shear in this rubber pads. And it is 200 millimeter, and across, if you see in this way, you can see 150 millimeter depth, and the thickness of these rubber pads happens to be 12 millimeter. Okay, so it moves like this. We will go once again. It moves like this. So when it moves, this is a kind of deformation it's going to cause. It's going to move like this, and owing to that kind of a movement, it's going to cause some kind of a deformation. The point earlier was here, and it just dislocated over here, and so also the point at this extremity will be dislocated, and the positions of the points will change. And here it has been formalized. It is formalized, and this is the amount of dislocation at the one end and at the other end. Therefore, shear stress equal to P by 2. We have considered only one plate. Okay, we could have considered the other plate also, central place where P is applied. Then we would have considered two areas of cross section, because it is attached to two rubber pads. P by 2 divided by 200 into 150. It is the area over which shear force is applied, and it becomes 15 by 2 into 1000 to make it Newton divided by this area. So it gets us 0.125 MPa. On the other hand, shear strain is 0.125 divided by shear modulus of elasticity. It's given to be kilopascal. It's given to be kilopascal over here. Okay, 830 kilopascal. You need to convert into Newton per millimeter square. Okay, kilo, make it Pascal. Okay, and in order to convert this Pascal into millimeter square, because a Pascal is Newton per meter square, therefore it should be converted into Newton per millimeter square. Upon this conversion and upon simplification, we will get a shear strain value of 0.0125, and we will make the use of this shear strain in order to compute the horizontal displacement. Okay, the horizontal displacement x that happens over here can be calculated as shear strain is actually defined as h over this particular thickness, the amount of dislocation over this particular thickness or over this particular height. Therefore, and we know the shear strain value calculated here in the previous computation. So it is 0.10125 equal to x, the magnitude of dislocation divided by the height, that is 12 millimeter of the thickness. So x equal to 12 divided by this, it will give us the dislocation of 0.15 millimeter. A brass bar. This is an example. Okay, first of all, let us read the problem. A brass bar of length 2.25 meter with a square cross section, something like this, of 90 millimeter each side is subjected to an axial tensile force of 1500 kilonewton. Assuming that E equal to 111,110 GPa and mu Poisson's ratio being equal to 0.34, determine the increase in the volume of the bar. This problem typically explains that due to Poisson's effect, there will be changes in the volume too, however small it may be. This problem also throws light on as to why mechanics of materials should be called mechanics of deformable bodies, and we will compute this. So this problem has the concept of lateral strain, linear strain. The strain happens along the longitudinal axis is linear, and the strain that happens across the width and across the breadth is lateral strain. We will first of all calculate the initial volume. Initial volume is the length 2.25 into 1000 to make it millimeter, 90 into 90 already given in millimeter. So this gives us a volume of this particular entire bar is something like this. Okay, and it can be expressed succinctly as 1.82 into 10 to the power of 7 millimeter cube. Normal stress in this bar is 1500, make it Newton, divided by 90 by 90, and the area of cross section is square in nature, therefore 90 by 90, 90 into 90, that will give us a normal stress of 185.18 MPa. So normal strain or longitudinal strain, the strain that happens in this direction is 185.18 divided by the elastic modulus. The elastic modulus is 110 GPa, multiply by 10 to the power of 3 or 1000 to make it MPa. So we will get the longitudinal strain to be 1.683 into 10 to the power of 3 units, and it has no units, of course. Lateral strain is a function of longitudinal strain, but it should be multiplied by a factor. That factor is none other than the Poisson's ratio. So Poisson's ratio, the meaning of Poisson's ratio being 0.34 is the lateral strain is 34% of the longitudinal strain. That is the way we have to understand. This problem is also a pointer to understand lateral strain is too small a quantity in compared with the longitudinal strain. Of course, strain is already a too small a quantity, but having said that, the lateral strain becomes much meeker. Okay, so 0.34, this Poisson's ratio into this longitudinal strain will get us the lateral strain. Lateral strain can be expressed as dB by B or dd by D, and here, since it is a square section, dB by B would be enough. So change in length is epsilon into L. So that gives us change in length. Earlier length was 2.25 meters, and we multiply by longitudinal strain, we will get change in length. Change in length is 3.786 millimeter, or the amount of elongation is 3.786 millimeter. Therefore, changed length is the earlier length 2.25 meter or 2250 millimeter plus 3.786. So length goes for an increase. On the other hand, change in width is lateral strain into original width. So lateral strain is estimated to be this much, multiply by 90, so that will get us what is the change in width? 0.052. Since it is a lateral strain, it has to go for a decrease. The original width is going to will be decreased to an extent this much. So it becomes 89. It is no longer 90 millimeter. It is 89.95. We may argue that it is a too small a quantity. Yes, strains are too small a quantity only, but it incurs huge amount of stress. Stress is important for us because all the designs, be it a machine component or be it a structural component, is stress based. That too, working stress based. So final volume therefore equal to 2253.8 owing to change in the increase in length, and the width, decrease in the width, it is another width because the section is square in nature, and we will get the changed volume, which is this much, and it is little bigger than the original volume. Therefore, increase in the volume is the increased volume minus the original volume, which will give us 10,501.4 millimeter cube. Therefore, when a component is elongated with the help of a tension force or owing to a tensile force, its volume increases a bit. And we will take on to the concept of volumetric strain in the further tutorials. Next, the 14th question is about an elastomeric bearing pad consisting of two steel plates, one above and one below, bonded to a chloroprene elastomeric, which is used as a bearing for bridges. It's kept over here, and this is the bridge superstructure at the supporting position, and this is the pier top. or the column top or the abutment top or whatever. It is subjected to shear force V during standing static loading test. The pad has dimensions A equal to 125 millimeter, B equal to 240 millimeter, and the elastomer has the thickness of T 150 millimeter. 50 millimeter. When the force V equals to 12 kilonewton, the top plate is found to have displaced laterally by 8 millimeter with respect to the bottom plate. What is the shear modulus of elasticity G of chloroprene? With this problem, we are finding important property of elastomer, that is the rigidity modulus. Cross section of the bearing component. Okay, this problem explains the Poisson's effect, changes in volume. Okay, and this problem particularly is directly puts SOM, strength of materials, into a real world application. Okay, we will find elastomeric bearings under the bridges at the bridge supports, and we will list all the values given. Shear force is 12 kilonewton, therefore 12,000 newton. A and B, the dimensions of the elastomeric bearing, 125 millimeter, 240 millimeter, and thickness is 50 millimeter, and amount of dislocation is 8 millimeter. Therefore, we can calculate the average shear stress being V divided by area of cross section. V is 12,000, area of cross section is 125, or resisting area. Instead we are not cutting the elastomeric bearing. Instead, it is a resisting area. It should be read as a resisting area. 125 by 240, it will give us a 0.4 MPa. Average shear strain, on the other hand, is this is the dislocation, 8 millimeter due to this particular shear force, and this is the height. And this dislocation happens over a thickness of 50 millimeter. Therefore, shear strain can be directly read as D by T, 8 by 50, that is 0.16. Shear modulus is a direct relationship between tau and shear strain. Tau is shear stress, gamma is shear strain. So shear stress is 0.4 and shear strain is 0.16. That gives us G of 2.5 MPa. Okay, the cross section of concrete corner column that is loaded uniformly in compression is shown in figure. Determine the average compressive stress, sigma C should have been, in the concrete if the load is equal to 7.5 meganewton. Determine the coordinates x and y of the point where the resultant load must act in order to produce uniform normal stress in the column. Of course, this concept has been told very clearly in our first tutorial itself. However, this problem, as a repetition, this problem helps us to understand the concept that irrespective of shape of cross section of a load bearing component like a column, like a beam, or a machine component, a column here, of course, the fact is that the load should be placed in alignment with the axis that passes through the centroid of the cross section, or hence CG of the component. Centroid is for a plane area, center of gravity is for a component. Therefore, area of cross section can be computed. It is 0.9 into 0.9. This square component, it's a composite cross section, of course, and 2 quadrant of circles over here. Okay, here at the corners, 2 into 1/4 of pi r square. R is 0.3 meters. Okay, and the small square that comes over here, that is 0.3 into 0.3, because this particular cross section is made out of a big square measuring 0.9 by 0.9 and 2 quadrant of circles and one small, let us say, a square which is hidden in between, which is sandwiched between these 2 quadrant of circles, 0.3 into 0.3. So that gives us the area of cross section to be 1.0413 meters square. Therefore, multiply by 1000 into 1000 to make it millimeter square. So that multiplies with a factor 10 to the power of 6. Right. the column is like this in reality, and we need to place the load over here exactly at the center of gravity or along the axis which passes through the centroid of area of cross sections, because you can understand that this particular column is made out of arrangement of innumerable number of cross sections like this in a height wise fashion. So a column is constructed. Therefore area of cross section really matters, because we need not have to take into account the entire length of the component. Right. Normal stress is 7.5 into 10 to the power of 6, the applied load divided by area of cross section, so that will get us 7.2 MPa. And this cross section is made out of a square cross section, as I told earlier. Add to that a small square, add to that 2 quadrant of circles. So therefore we need to find out the location. Of course this cross section is symmetrical with respect to x, therefore we need to find out x bar. Y bar need not have to be found because it is 45 millimeters. And in order to find this, we will recall our memory in strength of material, in mechanics of engineering mechanics, wherein we knew as to how we can calculate the centroid of a section. It is moment of the entire area with respect to a axis divided by the area. Okay, I repeat, the centroidal location is given by a common formula or formulation which runs something like this. It is the moment of the entire area with respect to a reference axis divided by area of cross section, total area of cross section. Therefore we will take moment of elementary areas with respect to y axis. Elementary area is a square, 0.9 into 0.9, its center of gravity centroid is at 0.45 from this axis. And as far as these 2 quadrants of a circles are concerned, its area is 2 quadrants of circles, 2 pi r square divided by 4 into the centroid is somewhere over here, 4r by 3 pi, 4r by 3 pi. Okay, here till here, but we need to measure up till here, therefore it is plus 0.9. So from here till here it is 4r by 3 pi plus 0.9. And as far as this square is concerned, it is 0.3 into 0.3 area, and here till here it is 90 or 0.9 plus 0.15. That makes it 1.05, and upon simplification we will get moment of the elementary areas is 0.603 divided by total area. Just now we have found out it is 0.58 meters. Therefore this is the centroidal distance, and here exactly we need to place the load in order to obtain the heart of the matter is in order to obtain uniform stress distribution across the cross section of the column. Friends, with this we have come to a closure of the 5th tutorial, and in this tutorial we discussed problems of moderate complexity, but we just chosen the examples from the real world in order to put this fantastic subject in a place of sanctity. I think it is not wrong or it is not exaggeration if I just express that strength of materials or mechanics of materials is bread and butter for mechanical engineers, industrial production engineers, aeronautical engineers, and as well as civil engineers. So with this I am going to close this session. If you have not subscribed to my channel, and if you liked this video, kindly subscribe to my channel. Until I come out with the problems of little complexity, higher complexity. Until then, I bye and thank you.